Imagine for a moment that you could see the universe not as it appears to the naked eye, a scattering of stars across a dark field, but as it truly is, a vast three-dimensional architecture of light and matter, stretching in every direction for billions of light years. Galaxies clustered along filaments like dewdrops on a spider's web, voids of nearly empty space between them, wider than the mind can comfortably hold. Now imagine, within this architecture, a single object, not a star, not a cluster, not even an ordinary galaxy, with its hundreds of billions of suns and its graceful spiral arms, or its soft elliptical glow. Something larger, something so large that to place it next to our own Milky Way, a galaxy that itself contains 200 to 400 billion stars, would be to place a coin beside a cathedral. This object exists. It has been measured. It has been observed. And in 2022, a team of astronomers confirmed what their data had long suggested, that it is the largest known galaxy in the observable universe. Its name is Alcyoneus. Tonight, we journey to Alcyoneus, not with urgency or alarm, but with the patient, wondering attention that this extraordinary object deserves. We will explore what makes it so vast, how it came to be, and what it tells us about the nature of galaxies, of cosmic scale, and of the universe's capacity to build structures that dwarf all ordinary expectation. This is not a journey of fear. It is a journey of proportion, of learning to hold very large numbers and very ancient timescales with the same quiet equanimity with which the universe itself holds them. The cosmos is large. It always has been. Tonight, we simply appreciate how large. If you love exploring the cosmos, a like and subscribe would mean the world to us. Let's begin. Before we can truly appreciate Alcyoneus, we need to understand what a galaxy is, not merely as a word, a term we have heard often enough that it passes without friction through the mind, but as a physical reality, a thing made of specific components, held together by specific forces, existing on scales that require a patient effort to truly grasp. A galaxy is, at its most fundamental, a gravitationally bound system of stars, gas, dust, and dark matter. It is a community, enormous and ancient, of stellar objects that share a common gravitational center and move through space together, their individual orbits determined by the collective mass of everything within the system. Our own galaxy, the Milky Way, is a barred spiral galaxy. Seen from above, it would appear as a disk of stars with curved arms spiraling outward from a central bar. At its heart lies a supermassive black hole called Sagittarius A star, containing approximately 4 million solar masses. Around the central bar, two major spiral arms sweep outward, populated with young stars, star-forming regions, and the gas and dust from which new stellar generations are constantly being born. The Milky Way is large. It spans approximately 100,000 light-years from edge to edge. A light-year, the distance light travels in a single year, is approximately 9.5 trillion kilometers. To cross the Milky Way at the speed of light would take 100,000 years. We tend to think of this as large. And within our immediate frame of reference, it is. But galaxies come in an enormous range of sizes. Dwarf galaxies, the most common type, may contain only a few hundred million stars and span a few thousand light-years. Giant elliptical galaxies can contain trillions of stars and stretch across hundreds of thousands of light-years. And then there are the giants among giants, objects like Alcyoneus, which redefine what the word large can mean. The universe's galaxies are not all alike. They come in a range of shapes and sizes and states of activity that reflect their different histories, their different environments, and the different fates that await them. The most familiar type, the one that captures the imagination most readily, is the spiral galaxy. Spirals are characterized by their disc-like structure and their sweeping arms, where star formation is ongoing and young. Hot, blue stars illuminate clouds of gas. The Milky Way is a spiral. So is the Andromeda galaxy, our nearest large neighbour, approximately 2.5 million light-years away. Spirals tend to be relatively rich in gas and dust, the raw material for ongoing stellar birth. Elliptical galaxies are different in character, rounder or more oval in shape, with little internal structure. They contain mostly older, redder stars and relatively little gas or dust. Star formation in ellipticals has largely ceased. They are, in a sense, the elder population of the galactic world, their active star-forming years behind them, their stellar populations aging slowly toward a quieter equilibrium. The largest galaxies in the universe tend to be ellipticals. Lenticular galaxies occupy a kind of middle ground, disc-shaped like spirals but without prominent spiral arms, and with the older stellar populations characteristic of ellipticals, they appear to be spirals that have used up their star-forming gas. Then there are irregular galaxies, asymmetric, lacking clear structure, often the result of gravitational interactions with neighbours. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, visible as bright patches in the southern sky, are irregulars, their shapes disturbed by their gravitational relationship with our much larger galaxy. Each type tells a story. Each reflects a history of formation, interaction, and evolution stretching back billions of years. Alcyoneus belongs to a category that will take us several segments to fully explore. It is, in technical terms, a radiogalaxy, an active galaxy with jets of plasma extending far beyond its stellar body. It is also, by measurement, the most spatially extended galaxy ever confirmed. Its story encompasses all of these galactic types and surpasses them. To understand Alcyoneus fully, we need to understand what a radiogalaxy is, because it is not the visible stars of Alcyoneus that make it so extraordinarily large. It is something else entirely, something that extends far beyond the galaxy's stellar body into the surrounding space. Radiogalaxies are a class of active galaxies whose most prominent feature is not visible light but radio waves, long wavelength electromagnetic radiation, emitted by charged particles moving at near the speed of light. These particles are launched by the supermassive black hole at the galaxy's centre, not consumed by the black hole, but expelled along its rotational axis in two powerful collimated jets. These jets are among the most energetic phenomena in the universe. They carry material, primarily electrons and protons, at velocities approaching the speed of light, driving it outward from the galactic centre for distances that can far exceed the extent of the visible galaxy itself. When these jets eventually encounter the more diffuse gas of the intergalactic medium, the thin material that fills the space between galaxies, they slow, spread, and form vast, diffuse lobes of radio-emitting plasma. These lobes are called radiolobes, and in the case of the largest radiogalaxies, they can extend for millions of light-years. The jets and lobes of a radiogalaxy are invisible to the human eye. They emit no visible light, but to a radio telescope, an instrument designed to detect electromagnetic radiation in the radio portion of the spectrum, they glow brightly, enormously. Their extent reveals itself in radio maps as two great lobes bracketing the visible galaxy at their centre. Radiogalaxies have been known and studied since the mid-20th century, when the development of radio astronomy first revealed the sky's invisible architecture. Some of the first radio sources to be identified, Cygnus A, Centaurus A, were radiogalaxies whose extraordinary energy output puzzled astronomers until the physics of active galactic nuclei and relativistic jets was understood. Alcyoneus is a radiogalaxy, the most extended radiogalaxy ever measured. The confirmation of Alcyoneus as the largest known galaxy came from a team of researchers led by Milky Way and colleagues at Leiden University in the Netherlands, published in the journal Astronomy and Astrophysics in 2022. The discovery was made possible by the Low-Frequency Array, LOFAR, a network of radio telescope stations spread across Europe, centred in the Netherlands. You've had that together function as an extraordinarily sensitive and high-resolution radio observatory. LOFAR operates at low radio frequencies, making it particularly well-suited to detecting the diffuse, aging radio lobes of giant radio galaxies whose emission has faded and stretched over billions of years. In a careful analysis of LOFAR survey data, the LOFAR 2-meter sky survey, which is systematically mapping the radio sky at unprecedented sensitivity, OE's team identified a radio source of exceptional extent, a pair of radio lobes separated by a distance that, once the source's redshift was measured and its distance calculated, translated to a physical extent of approximately 5 megaparsecs. 1 megaparsec is approximately 3.25 million light-years. 5 megaparsecs is therefore approximately 16.25 million light-years. The Milky Way, spanning 100,000 light-years, would fit within Alcyoneus more than 160 times along its longest axis alone. The source was identified as a galaxy, visible in optical imaging, at a redshift corresponding to a distance of approximately 3 billion light-years from Earth. The galaxy itself, the stellar body at the centre of this vast radio structure, is not particularly unusual in its optical appearance. It is a large elliptical galaxy, as expected for a radio galaxy host. But the jets it has launched, and the lobes those jets have inflated over billions of years, are without precedent in known scale. The team named the source Alcyoneus, after the giant of Greek mythology, son of Gaia, and Earth itself, who, in legend, could not be defeated while he remained in contact with the ground. The name, in its mythological resonance, feels appropriate. This is a giant of the cosmic ground. Let us sit with the scale of Alcyoneus for a moment, not hurrying past it, simply attending to what these numbers mean, as honestly as we can. Alcyoneus, from the tip of one radio lobe to the tip of the other, spans approximately 16.3 million light-years. This is the distance that light, travelling at 300,000 kilometers per second, would take 16.3 million years to cross. To put this in terms of familiar astronomical distances, the distance from the Milky Way to the Andromeda galaxy, our nearest large neighbour, and 2.5 million light-years away, is roughly 1/6 of Alcyoneus's total extent. Alcyoneus is more than 6 times wider than the gap between our galaxy and our nearest galactic neighbour. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and several dozen smaller satellites, spans approximately 10 million light-years. Alcyoneus is wider than the entire local group. The Virgo cluster, the nearest large galaxy cluster, containing over 1,300 galaxies, sits approximately 53 million light-years from Earth. Alcyoneus, were it placed at one edge of the Virgo cluster, would extend nearly 1/3 of the way to us. These are not merely large numbers. They represent a physical structure, plasma, magnetic fields, streaming particles, that actually exists right now. In the universe. Not a theoretical construct, not a simulation. A real object measured by real instruments, extending across a volume of space that makes almost everything else in the known cosmos seem compact by comparison. The visible galaxy at Alcyoneus's centre, the stellar body, the elliptical conglomeration of stars, spans perhaps 500,000 light-years, already 5 times the Milky Way's diameter, but the radio lobes that bracket it extend 8 million light-years on each side, dwarfing the galaxy they belong to as ocean dwarfs an island. Alcyoneus is, in the most literal sense, the largest known structure produced by a single galaxy. How does a galaxy grow radio lobes 16 million light-years across? The answer lies in time, in energy, and in the particular environment that Alcyoneus inhabits. At the centre of Alcyoneus is a supermassive black hole. All large galaxies are believed to harbour such objects, collapsed remnants of ancient mass accumulation, containing anywhere from millions to tens of billions of solar masses. The black hole at Alcyoneus's centre is actively accreting, drawing in surrounding material in a process that releases enormous quantities of energy. As matter falls toward the black hole, it forms an accretion disk, a swirling, superheated structure that radiates brilliantly. Powerful magnetic fields generated by the moving charge particles in this disk interact with the black hole's spin and launch twin jets of plasma perpendicular to the disk, upward and downward, away from the galactic plane. These jets travel at velocities that are significant fractions of the speed of light. They carry kinetic energy and magnetic energy outward from the galaxy's centre, piercing through the interstellar medium of the host galaxy and continuing into the intergalactic medium beyond. For Alcyoneus, this process has been ongoing for an extraordinarily long time. The immense extent of its radio lobes implies that its jets have been active, pumping energy outward, for hundreds of millions of years or longer. Over that time, the lobes have expanded, driven by the jet energy, inflating like enormous bubbles in the tenuous intergalactic gas. But the size of those lobes is not determined solely by the jet power. it is also profoundly influenced by the environment. In dense cosmic environments, near the centers of galaxy clusters, where the intracluster medium is rich and pressure-filled, radio lobes are compressed. They cannot expand freely. The pressure of the surrounding gas holds them back. Alcyoneus appears to inhabit a particularly underdense region of the cosmic web. The intergalactic medium around it is thin, less material, lower density, lower pressure. The jets and lobes, finding little resistance, have been free to expand to remarkable dimensions. In this sense, Alcyoneus's extraordinary size is a product of both internal energy, the persistent activity of its central black hole, and external environment, the sparse, low-pressure void that allows its lobes to spread without restraint. Vastness, here as elsewhere in nature, is partly a matter of freedom. Let us take some time to understand the engine at Alcyoneus's heart, because the supermassive black hole that powers this extraordinary object is, in its own right, one of the most remarkable phenomena in the universe. Black holes as a concept are often approached with a kind of ambient unease, the idea of an object from which nothing can escape carrying an intuitive weight that can feel unsettling. But in the scientific context, black holes are simply objects, extraordinarily dense concentrations of mass with gravitational fields strong enough to prevent light from escaping beyond a certain boundary, called the event horizon. Supermassive black holes, those containing millions or billions of solar masses, reside at the centers of most large galaxies. They formed through a combination of pathways: the direct collapse of massive gas clouds in the early universe, the growth of stellar mass black holes through repeated mergers and accretion, and the merger of galaxies whose central black holes eventually coalesced. When a supermassive black hole is actively accreting material, pulling in gas and dust from its surroundings, it becomes what astronomers call an active galactic nucleus, or AGN. The energy released by this accretion process can outshine the entire galaxy of billions of stars that surrounds it. The most luminous AGN, quasars, are detectable at cosmological distances, their brilliant light outrunning the dimmer glow of their host galaxies. The jets produced by AGN, the collimated streams of plasma that create radio lobes in radio galaxies like Alcyoneus, represent a fraction of the energy that the accretion process releases, channeled by magnetic fields into a focused, directed outflow. The physics of jet launching is still an active area of research, but the general framework is understood. Rotating black holes, combined with the magnetic fields generated by infalling material, produce a natural mechanism for extracting rotational energy and channeling it into outflowing plasma. The black hole at Alcyoneus's center has been doing this, steadily, persistently, over timescales we can barely imagine, for long enough to inflate lobes the size of 6 local groups. That persistence is its own kind of profound. Radio lobes are not static. They are dynamic, evolving over time as the jet continues to pump energy into them, as the surrounding gas pushes back, and as the high-energy electrons within them gradually lose their energy to radiation. In the early phase of a radio galaxy's life, the jets are young and energetic. They punch through the interstellar medium of the host galaxy and begin to inflate lobes in the intergalactic medium beyond. The plasma within the lobes is rich in high-energy electrons, emitting brightly at radio frequencies. This is a radio galaxy in its active, bright youth. Over time, over tens and hundreds of millions of years, several things change. The jets may fluctuate in power, or temporarily shut off entirely, as the accretion rate at the central black hole varies. The electrons within the lobes gradually radiate away their energy, a process called synchrotron cooling, shifting their emission toward lower and lower radio frequencies, as the highest energy electrons are depleted first. This means that older radio lobes, like those of Alcyoneus, emit preferentially at lower radio frequencies. This is one reason why LOFAR, a low-frequency radio array, is particularly well suited to finding the oldest and most extended radio structures. Instruments optimized for higher radio frequencies would miss the aged, faded emission that traces the full extent of objects like Alcyoneus. The discovery of Alcyoneus's true size was, in part, a technological achievement, made possible by an instrument sensitive to precisely the frequencies where ancient, cooling plasma still faintly glows. Eventually the jets cease entirely. The black hole stops accreting, or accretes too little to power significant jets. The lobes, no longer fed, begin to fade, their electrons cooling, their radio emission dimming. Over hundreds of millions of years, the lobes mix with the surrounding intergalactic medium, their plasma dispersed. Their magnetic fields diluted. What remains is a memory in the gas, a subtle disturbance, a region slightly warmer and more magnetized than its surroundings, as the largest galaxy in the universe slowly, gracefully, dissolves its signature into the cosmos. The jets and radio lobes of galaxies like Alcyoneus are not merely passive structures. They interact with their environments in ways that have profound consequences for the gas that surrounds them, for the formation of stars in neighbouring regions, and for the overall ecology of the cosmic web. This process is called AGN feedback, and it is one of the most important mechanisms in the universe for regulating how galaxies grow. Here is the essential story. When a galaxy grows large enough, its central black hole becomes massive enough to launch powerful jets. Those jets push energy into the surrounding gas, heating it, displacing it, driving outflows that sweep gas out of the galaxy and into the surrounding intergalactic space. By removing or heating the gas that would otherwise cool and condense into new stars, the AGN essentially limits its own galaxy's further growth. It is a self-regulating mechanism, the galaxy's own power source acting as a thermostat. In the dense, hot gas of galaxy clusters, the intracluster medium, radio jets from the central galaxy can carve enormous cavities, pushing the hot gas aside in bubbles that later collapse and send ripples through the cluster gas like stones dropped in a pond. These cavities have been observed in X-ray images of galaxy clusters, their presence a visible record of the jet activity that created them. For Alcyoneus, in its underdense environment, the feedback operates differently. Without a dense surrounding medium to confine and heat, the jet energy goes primarily into expanding the lobes rather than heating local gas. The effect on the immediate environment may be more diffuse, a gentle compression of the surrounding intergalactic medium, a slight heating of the void around it, rather than the dramatic cavity carving seen in cluster environments. But the principle remains. Every radio galaxy, at whatever scale, is not merely a passive inhabitant of the cosmic web. It is an active participant, shaping, heating, displacing, influencing the gas that fills the spaces between galaxies, and thereby influencing indirectly the formation of future generations of stars and galaxies across the cosmic neighbourhood. Alcyoneus, the largest such object known, has shaped a volume of intergalactic space that no other single galaxy has matched. To understand why Alcyoneus grew so large, we need to understand where it lives. Because in the universe, location is not merely geography, it is destiny. The environment in which a galaxy resides profoundly shapes what it can become. The universe's matter is not uniformly distributed. On the very largest scales, hundreds of millions of light years and beyond, it is arranged in a structure called the cosmic web. Dense filaments of dark matter and gas connect nodes, galaxy clusters and groups, where matter has concentrated under gravity. Between the filaments lie enormous voids, regions of space relatively empty of matter, spanning hundreds of millions of light years. This architecture formed from the tiny density fluctuations of the early universe, the same variations that are imprinted in the cosmic microwave background. Over 13 billion years, gravity has amplified those fluctuations, drawing matter along the filaments and clearing the voids, weaving the web that structures the cosmos today. Galaxies inhabit this web in different ways. Galaxies and clusters, the densest nodes of the web, live in rich dynamic environments. They interact frequently with neighbours. They move through dense intracluster gas. Their evolution is shaped by these interactions. Galaxies in voids and in underdense regions between filaments live differently. They have fewer neighbours. The surrounding gas is sparse and low pressure. Their evolution proceeds more quietly, less disrupted. Alcyoneus appears to live in precisely such an underdense environment. Detailed analysis of its surroundings indicates that it resides in a region of the cosmic web where the density of matter is below average. Not in the deep interior of a void, but in a low-density region that provides unusually little resistance to its expanding radio lobes. This is why Alcyoneus is so large. It is not that its central black hole is necessarily more powerful than those of other giant radio galaxies. It is that the universe in this particular place gave it room to grow. The cosmic web opened a space, and Alcyoneus, over hundreds of millions of years, slowly, patiently filled it. Alcyoneus is the largest known galaxy, but it is not isolated in its category. It belongs to a class of objects called giant radio galaxies whose total extent, including their lobes, exceeds approximately 2 megaparsecs, or about 6.5 million light-years. These objects are, by any ordinary measure, enormous, and yet they have, until Alcyoneus, remained somewhat at the margins of cosmological discussion. Among the notable giant radio galaxies that preceded Alcyoneus in the record books is J 142-0-0545, a source that was, before 2022, considered the largest known radio galaxy, with an extent of approximately 4.5 megaparsecs, still roughly 15 million light-years. Then there was 3C236, another long-studied giant radio galaxy extending several megaparsecs, and NGC 6251, whose jets trace elongated structure across millions of light-years. Each of these objects was discovered through the patient work of radio surveys, their full extent sometimes not recognized until sufficiently sensitive instruments were trained on them. In many cases, the full spatial scale of a giant radio galaxy is only revealed when an instrument with sufficient sensitivity at low radio frequencies, like LOFAR, images the faint extended emission of aging plasma that less sensitive surveys missed entirely. This raises an important and genuinely interesting point. How many Alcyoneus-scale objects might be lurking, undetected in the radio sky, their ancient faded lobes below the sensitivity threshold of earlier surveys? LOFAR's ongoing 2-meter sky survey is providing, for the first time, the combination of sensitivity and sky coverage needed to systematically find them. Alcyoneus may not remain the record holder indefinitely. As surveys improve and the radio sky is mapped with increasing depth, larger structures may emerge from the noise. The universe, when examined with sufficient care, has a persistent tendency to exceed previous expectations. Giant radio galaxies like Alcyoneus are not merely curiosities, record holders in a catalogue of cosmic superlatives. They are windows into some of the most fundamental questions in astrophysics and cosmology. One of the most important of these questions involves the properties of the intergalactic medium, the thin, hot gas that pervades the space between galaxies. This medium is extraordinarily difficult to study directly. It is too diffuse and too hot to radiate visibly, and it reveals itself primarily through X-ray emission and through its effects on other phenomena, such as the Sunyaev-Zeldovich effect, a distortion of the cosmic microwave background caused by hot electrons. Radiolobe plasma, as it expands into the intergalactic medium, acts as a probe of that environment. The rate at which the lobes expand, their shape, the pressure within them, all of these carry information about the density and pressure of the gas they are pushing against. By carefully modelling the radio emission of giant radio galaxies, astronomers can infer properties of the intergalactic medium that would otherwise be inaccessible. Alcyoneus, with its extreme extent in a low-density environment, provides a particularly interesting case study. Its lobes have expanded into one of the least dense regions of the cosmic web that has yet been probed by radiolobe expansion. The properties of that void-adjacent environment, its density, its temperature, its magnetic field strength, can be estimated from the behaviour of Alcyoneus's lobes in ways that complement and extend other observations. There is also a connection to cosmological models of structure formation. Giant radio galaxies in underdense environments provide tests of our predictions for how matter is distributed on large scales. If the models predict a certain distribution of void density, and if giant radio galaxies are found in environments consistent with those predictions, that is a validation of the cosmological framework. If Alcyoneus's environment turns out to be more extreme than the models predict, more underdense, more void-like, that would be a data point worth examining carefully. The largest galaxy in the universe is also, in this sense, a scientific instrument, a natural probe of the cosmos's most diffuse and challenging environments. At the centre of Alcyoneus, at the heart of an elliptical galaxy already 5 times larger than the Milky Way, there is a black hole, a supermassive black hole of a mass that remains, as of current measurements, somewhat uncertain. This stellar body of Alcyoneus, the visible galaxy, the aggregation of hundreds of billions of stars, has a mass estimated at approximately 400 billion solar masses. This places it among the larger elliptical galaxies known, though not at the absolute extreme. There are elliptical galaxies in the nearby universe that contain significantly more stellar mass than Alcyoneus. The total mass of Alcyoneus, including its dark matter halo, the invisible scaffolding of dark matter that surrounds all large galaxies, is considerably larger. Most galaxies contain dark matter halos that are tens or hundreds of times more massive than their stellar content. For a galaxy of Alcyoneus' size, the dark matter halo likely represents the dominant contribution to the total mass. What is notable is that Alcyoneus' stellar mass, while large, is not as extreme as one might expect given the unprecedented scale of its radio lobes. Other giant radio galaxies with similar or greater stellar masses have not produced lobes of comparable extent. This confirms that it is the environment, the underdense cosmic location, rather than the raw power of the central engine, that is primarily responsible for Alcyoneus' record-breaking scale. The black hole at Alcyoneus' centre is presumably massive, likely several billion solar masses, as is typical for the central black holes of large elliptical galaxies. But we do not yet have a precise measurement. Future observations, particularly from facilities like the Event Horizon Telescope, which has successfully imaged the shadows of supermassive black holes in nearby galaxies, may one day reveal the properties of this central engine in greater detail. For now, the black hole at Alcyoneus' heart remains known primarily through its consequences, the jets it launched, the lobes it inflated, i.e. the 16 million light-year structure that is its most visible legacy. The large elliptical galaxy that hosts Alcyoneus did not spring into existence fully formed. Like all large galaxies, it grew over cosmic time through a combination of processes, gradual accretion of gas, and the mergers of smaller galaxies into progressively larger structures. Galaxy mergers are among the most dramatic events in the universe, though they unfold on timescales measured in hundreds of millions of years. When two galaxies approach each other under gravity and eventually collide, the stars within them do not typically collide directly. The distances between individual stars are so vast that stellar collisions during a galaxy merger are vanishingly rare. Instead, the galaxies interpenetrate, their stars following complex gravitational trajectories that gradually settle into a new, combined structure. During a major merger, vast amounts of gas are funneled toward the center of the combined system, triggering intense bursts of star formation and often fueling the central black hole, turning it on as an AGN. The central black holes of the two merging galaxies themselves eventually spiral together under dynamical friction and coalesce, producing a more massive central black hole and, in the process, emitting gravitational waves detectable in principle by instruments like LISA, the planned space-based gravitational wave observatory. Over cosmic time, through repeated mergers with smaller galaxies, a process called minor merging or galactic cannibalism, large elliptical galaxies grow steadily. Each accreted galaxy adds mass to the stellar halo of the host, building it slowly outward. The elliptical galaxy at Alcyoneus' core has likely undergone this growth process over billions of years. Its current stellar mass of approximately 400 billion solar masses is the accumulated legacy of many episodes of star formation, gas accretion, and galactic mergers stretching back to the early universe. Each merger, each accreted satellite, each new generation of stars formed from infalling gas. All of these are chapters in a history that now spans most of cosmic time. The galaxy we observe today is the cumulative outcome of that history. We have been speaking throughout this journey about distances and sizes that resist ordinary comprehension. 16 million light-years, hundreds of millions of years, are billions of solar masses. These numbers pass through the mind easily enough. We are accustomed to large numbers in science, but they do not naturally settle into felt understanding. Let us try once more to make the scale of Alcyoneus genuinely present. The speed of light is, to human experience, essentially instantaneous. Light crosses a room in a nanosecond. It circles the Earth in about 1/10 of a second. It takes 8 minutes to travel from the Sun to Earth. It takes 4 years to reach the nearest star, Proxima Centauri. Now, it would take 16 million years for light to cross Alcyoneus from one end to the other. 16 million years ago, on Earth, the Miocene epoch was in progress. Grasslands were spreading, early great apes were diversifying. The continents occupied positions close to but meaningfully different from today. The Himalayan mountains were still growing. Homo sapiens would not appear for another 15.5 million years. In the 16 million years that it takes light to cross Alcyoneus, the entire history of our lineage from proto-apes to modern humans, a history we consider ancient and deep, would pass multiple times over. This is the scale of Alcyoneus, not merely a large galaxy, a structure so vast that the entire span of human ancestry is a small fraction of the time that light takes to traverse it. The response that these proportions invite is not fear, and it is not insignificance. It is something more like wonder at the variety of scales at which the universe operates. At the fact that it contains both the synaptic gap in a sleeping mind, measured in nanometers, and Alcyoneus, measured in megaparsecs. The universe holds both simultaneously without contradiction. We are small. Alcyoneus is vast. The universe contains both without preference. Alcyoneus is not the only extreme in the universe. It is one entry in a catalogue of superlatives that, taken together, reveal something important about the character of the cosmos. The most massive known star, R13601, contains approximately 300 solar masses, shining with a luminosity perhaps 8 million times that of our Sun. The smallest known stars, red dwarfs near the boundary of stellar ignition, may contain only 8% of the Sun's mass. The most massive known black hole, TON 618, a quasar black hole, contains approximately 66 billion solar masses. The smallest stellar mass black holes likely contain only a few times the Sun's mass. The most distant confirmed galaxy, observed at a redshift corresponding to a time when the universe was only a few hundred million years old, existed nearly 13.5 billion years in the past. The nearest star system is 4 light-years away. The coldest natural environment known in space is the Boomerang Nebula, a planetary nebula roughly 5,000 light-years away, where expanding gas has cooled to approximately 1 degree Kelvin, above absolute zero. The hottest environments are the cores of supernovae and the collision regions of galaxy clusters, reaching billions and even trillions of degrees. The universe operates across ranges that dwarf anything in human engineering or human experience. It seems to explore its own parameter space, to test the limits of what its physics allows, with a thoroughness and variety that produces objects at every extreme the laws of nature permit. Alcyoneus is one of those extremes, the maximum spatial extent so far identified for a structure produced by a single galaxy. A test case for the conditions under which cosmic objects can grow largest. And somewhere in the universe, in regions not yet surveyed with sufficient sensitivity, there may be objects that exceed even this. Larger lobes, more ancient, more extended, waiting in the low-frequency radio sky for an instrument sensitive enough to reveal them. The universe does not quickly reveal its full catalogue of extremes. What will become of Alcyoneus over the vast stretches of future cosmic time? The radio lobes, as we have noted, will fade. The electrons within them, already old, already cooling, will continue to lose energy. The radio emission will shift to lower and lower frequencies and eventually fall below any reasonable detection threshold. The lobes will fade into the intergalactic medium, their plasma mixed with the surrounding gas, their magnetic fields diffused and weakened. This process will take hundreds of millions of years. On that time scale, the lobes will essentially disappear, not destroyed, but dispersed. The thermal energy they deposited in the surrounding gas will persist in subtle ways, slightly heating the intergalactic medium of the underdense region Alcyoneus inhabits. But the dramatic, i.e. the extended structure that makes Alcyoneus so remarkable today will be gone. The central galaxy, the stellar body of hundreds of billions of stars, will remain. Elliptical galaxies are stable structures. They do not have the ongoing star formation that renews spiral galaxies with fresh young populations, but they are long-lived. Their older, redder stars will shine, diminishing gradually as the most massive among them complete their stellar lives for billions of years. The central black hole may flare again, if a fresh supply of gas reaches it through a minor merger or through the cooling of gas in the surrounding medium. If it does, new jets may form, new lobes may begin to inflate. A radio galaxy can experience multiple episodes of activity, old, faded lobes from earlier periods sometimes visible alongside younger, brighter ones. A palimpsest of AGN activity written in the low-frequency radio sky. Or the black hole may fall quiet. The accretion rate may decline below the threshold needed to sustain significant jets. The galaxy may enter a radio quiet phase, still massive, still ancient, but no longer broadcasting. What will certainly continue is the cosmic expansion. The universe's accelerating expansion means that the intergalactic medium around Alcyoneus will become progressively more dilute over cosmic time, as space stretches and the density of matter decreases. The environment that allowed Alcyoneus's lobes to grow so vast will become, in the deep future, even less dense, though by then, the lobes will long since have faded. In the very deep future, in timescales measured in trillions of years, even the stars within Alcyoneus's central galaxy will have exhausted their hydrogen fuel. The galaxy will become a collection of stellar remnants, white dwarfs slowly cooling to darkness, neutron stars spinning down their rotation, black holes accumulating the last traces of available matter. The record holder of today will, in the deep future, be quiet, dark, and ancient beyond all current human reckoning. But for now, in this brief, bright era of cosmic history, it burns with the activity of an ancient, extraordinary object, broadcasting its presence across the radio sky for anyone patient enough to listen. The discovery and study of Alcyoneus has contributed to our understanding of galaxies in several concrete ways. Let us spend a moment considering these contributions, not as a list of achievements, but as a coherent picture of what this single extraordinary object has illuminated. First, Alcyoneus has confirmed that the physical extent of giant radio galaxies is more strongly influenced by environment than by intrinsic AGN power. This is a significant insight. Previous discussions of giant radio galaxy formation had sometimes focused primarily on the power of the central engine, assuming that larger lobes required more powerful jets. Alcyoneus's case, where the stellar mass and likely black hole mass are not uniquely extreme, but the environment is unusually sparse, shifts the emphasis. Environment is not merely a secondary factor. In the right cosmic conditions, it is the primary driver of the most extreme spatial scales. Second, Alcyoneus has provided a new probe of the low-density intergalactic medium in a void-adjacent environment. By modelling the expansion and emission of its lobes, astronomers can constrain the properties of the surrounding gas in a region that is otherwise extremely difficult to study. This contributes to our understanding of the cosmic web structure in its least dense regions. Third, the discovery demonstrates the scientific value of low-frequency radio surveys like LOFAR. Giant radio galaxies, and the largest ones in particular, may have been systematically under-detected in previous surveys due to sensitivity limitations at low frequencies. The LOFAR 2-meter sky survey may reveal more objects of this class, potentially including objects even larger than Alcyoneus. And fourth, perhaps most broadly, Alcyoneus reminds the scientific community that our catalogue of the universe's most extreme objects is not yet complete. The largest, the most massive, the most extended, these categories remain open. Each generation of instruments pushes the boundaries of what is detectable and consistently finds things that previous generations could not see. The universe is larger and stranger than each previous chapter of our understanding has captured. This is not a failure of science. It is the nature of a universe that genuinely exceeds, again and again, the limits of what we thought was possible. There is a question worth sitting with quietly as we near the end of our journey tonight. Why do we study objects like Alcyoneus? What draws the human mind, a mind that evolved to navigate the scale of a single planet, a single landscape, a single lifetime, toward the study of things 16 million light-years wide? The practical answers are genuine. Giant radio galaxies tell us about AGN feedback, about the intergalactic medium, about the structure of the cosmic web. They are scientifically valuable. Their study advances our understanding of how the universe's larger structures form and evolve. But there is something beyond the practical, something in the act of comprehending extreme scale that serves a purpose the practical justification does not fully capture. When we genuinely attend to the scale of Alcyoneus, when we do not merely read the numbers but try, however incompletely, to feel them, something shifts in our relationship with our own situation. The concerns that fill an ordinary day find their natural proportion, not dismissed, not invalidated, but placed momentarily in a context so large that they occupy their true fraction of the universe's attention, which is, of course, essentially zero. This is not nihilism, it is perspective, and perspective, chosen deliberately and held with care, is one of the most genuinely useful things a human mind can cultivate. The universe does not need us to understand Alcyoneus. The galaxy existed, vast, ancient, broadcasting, long before there were minds to observe it, and will continue long after we have gone. But we, in understanding it, become briefly larger than ourselves. We hold in our minds something that contains our entire civilization as a footnote. That expansion of self, that momentary participation in the scale of the cosmos, is, I would suggest, one of the most valuable experiences that science makes available to us. It is not frightening. It is generous. As we approach the final thoughts of our journey tonight, let us take a moment to appreciate where we stand in the history of cosmic understanding. We are living through an era of extraordinary observational capability. Radio telescopes like LOFAR are mapping the low-frequency sky with sensitivity and resolution that would have been impossible a generation ago. The James Webb Space Telescope is revealing the universe's first galaxies and the atmospheric chemistry of distant worlds. The Vera C. Rubin Observatory is beginning its decade-long survey of the southern sky, building data sets of unprecedented depth. Gravitational wave observatories are opening an entirely new observational window, detecting the ripples in space-time produced by merging black holes and neutron stars. In this environment, discoveries like Alcyoneus are not isolated surprises. They are symptoms of a general deepening, a broadening of our cosmic inventory as instruments improve and surveys cover new ground. What will the next generation of radio surveys reveal? How many Alcyoneus-scale objects are lurking in the faint low-frequency sky, undetected because previous instruments lacked the sensitivity to find them? Are there radio structures larger than Alcyoneus, 17, 18, 20 million light-years across, waiting to be uncovered? These are genuinely open questions. The answers depend on survey sensitivity, survey sky coverage, and, ultimately, on what the universe actually contains. It may be that Alcyoneus is genuinely near the upper limit of what a single radio galaxy can produce, or it may be that the universe, as usual, has further surprises in store. Either way, the work continues, the telescopes point, the data accumulates, the patient, methodical process of expanding human knowledge moves forward, not quickly, not dramatically, but steadily and honestly, as it has always done. And in that ongoing work there is a kind of beauty that is different from the beauty of individual discoverers. It is the beauty of a sustained collective human effort to understand the cosmos, carried forward by each generation, passed on to the next, never quite finished, always moving deeper, somewhere in the universe. 3 billion light-years from the planet where these words were written and these thoughts were gathered, there is a galaxy. It is not the most massive galaxy. It is not the youngest, nor the most active, nor the most luminous, but it is the most spatially extended structure that a single galaxy has yet been confirmed to produce. Its radio lobes extend in 2 great arcs to a total span of 16.25 million light-years. Right now, or rather, as the light that we observe left it, 3 billion years ago, it is doing what it has been doing for hundreds of millions of years. The central black hole is accreting, slowly or rapidly, drawing in material and converting its gravitational energy into the kinetic and magnetic energy of jets. Those jets are pushing outward, through the sparse intergalactic gas of its underdense cosmic neighborhood, adding, by the smallest imaginable increments, to the already extraordinary extent of its lobes. It does not know it is the largest. It does not know it has been measured. It has no awareness of the radio telescopes in the Netherlands whose data revealed its true scale, or of the paper published in 2022 that gave it a name, Alcyoneus, drawn from the mythology of a civilization that exists from its perspective in a galaxy 3 billion light-years away on a small rocky planet orbiting an ordinary star. The universe contains many such asymmetries, objects of extraordinary scale that have no awareness of their own extraordinary nature, and minds of extraordinary small scale, brief, soft, curious, that have somehow developed the capacity to measure them, name them, and wonder at them. We are those minds, small, brief, curious, evolved to navigate a single planet but driven by some insistent quality of human consciousness to reach outward, to measure what we cannot visit, to name what we cannot touch, to find, in the act of understanding something 16 million light-years wide, something that feels like kinship with the cosmos. That kinship is not an illusion. We are made of the same physics that governs Alcyoneus. The electrons that carry thought through our neurons are the same particles that spiral in the magnetic fields of its radio lobes, emitting in frequencies we have learned to detect. The forces that bind our atoms are the same forces that shape the jets that inflated its lobes over hundreds of millions of years. We are not separate from the universe we study. We are part of it, a small, young, temporary and somehow extraordinarily self-aware part of it. The largest galaxy in the observable universe drifts in its low-density region of the cosmic web, broadcasting at low radio frequencies, its lobes expanding by fractions too small to measure against any human timescale. It is patient in the way that only something governed by cosmological physics can be patient, not choosing patience, not cultivating it, but simply operating on timescales so vast that what looks like patience from our perspective is simply the pace at which it lives. We can, if we choose, borrow something from that pace tonight. Let the numbers settle without rushing. Let the scale be large without demanding that it be made small. Let the mystery remain mysterious, because mystery, held without urgency, is not a problem to be solved, but a quality of reality to be inhabited. The universe is large. It has always been large. We have simply been learning, slowly and carefully and with increasing precision, exactly how large. Alcyoneus is the current frontier of that learning in one particular dimension. Tomorrow, or next year, or in a decade, another survey will reveal another record. The frontier will move. The universe will, once again, exceed the limits we had placed on it. And that persistent, faithful, gentle exceeding of expectation is perhaps the most characteristic thing about this cosmos we inhabit. Thank you for spending this evening in its company, for travelling, in thought and in wonder, to the edge of what is known. Rest now. The universe does not pause in its work. Telescopes continue to observe, and the data continues to accumulate, and Alcyoneus continues its slow, vast existence 3 billion light-years away. But you may rest. The largest thing we know is already exactly what it is, enormous, ancient, and entirely at peace with its own scale.